Hello everyone, my name is Matt V. Poliszczuk, and in this video I'll be going over the MEXT Undergraduate 2019 physics exam. So the way this will work is for every question I will start by just telling you what you need to know to be able to answer it so you can try it on your own, and then I will go through the detailed step by step. But before that though, I just want to mention a few things about the exam that I think are important to know. So it's written on the exam that it is 1 hour long, and you cannot bring a calculator or any other tools, just writing utensils. One thing that I didn't know when I went to write the exam is that they do not give you any extra writing space. No scrap paper, anything. So the only space you have to work is the margins of the exam sheet itself. So when you're practicing for this exam, make sure to keep in mind that you don't have much space to do your work. And at least in my case, the exam was printed on both sides of the page. So there was no, blank side on the back to work on. Now, thankfully for physics, that usually isn't much of a problem since it's quite spread out over a lot of pages, so you do end up with a lot of space. That's more so an issue for math and maybe chemistry. And also, briefly, I will summarize the units of physics that you need to know to do this exam. So there's always a long-form question on kinematics, thermodynamics, and waves/optics. Then there's also a question related to electricity, though it varies on the exact topic. So sometimes it can be something like electric and magnetic fields, or it can be circuits. Also, sometimes you get questions on gravitational motion, things like Newton's law of gravitation, escape velocity, radius of orbit, just the kind of standard physics gravity problems you can get in high school. But to be very clear, I don't actually know the exact physics curriculum in Japan. This is just the observation that I made from looking through all of the former practice exams. So with that out of the way, let's start with the exam. First is section 1, which is a series of small questions on a variety of physics topics. And the first one is question 1, which says, a car at rest starts moving along a straight line and stops at time t equals 80 seconds. The velocity v of the car changes as a function of time t, as shown in this figure. Find the distance that the car travels. So for this, all you need to know is that the integral of a velocity over time graph gives you a displacement over time graph. Or more simply, the area underneath the curve on a velocity time graph gives you the displacement over time. So here, all you need to do is find the area underneath this curve. And thankfully, that's very simple. It's just some simple shapes. We have 2 triangles and 1 rectangle, and they give you all the exact values, all the heights and widths and whatnot. Or, if you wanted to, you could find the whole area of the trapezoid at once. Either way, it's pretty easy. And you get that it equals to 3,000. So the distance that the car has traveled is 3,000 meters, which is the answer C. Okay, so next is question 2, which says, a small ball at rest falls down from a height of h above the ground and bounces repeatedly. The coefficient of restitution between the ball and the ground is denoted as E, and the acceleration of gravity as g. Find the maximum height of the ball between the nth and the n+1th impact with the ground. So for this question, you need to know what a coefficient of restitution is. And I never learned that in school, so it may be unfamiliar to you as well. But basically, the coefficient of restitution is the ratio of the momentum of an object right after and right before a collision. So it's equal to P sub f over P sub I, where f is final and I is initial. And this measures how elastic a collision is. If a collision is perfectly elastic, then the momentum after the collision will equal to the momentum before the collision, and so the coefficient of restitution will be equal to 1. But if it's not perfectly elastic and some momentum is lost, then the coefficient will be less than 1. So this is a value between 0 and 1. Now, assuming the mass doesn't change, which in this case it does not, the coefficient of restitution can be expressed as just velocity final over velocity initial, since momentum is equal to mass times velocity. Then, because in this case we're talking about a ball falling, we can write velocity in terms of the height that the ball is dropped from. And this comes from relating gravitational potential energy to kinetic energy. So at the start, the ball is dropped from rest, so all its energy is in the form of gravitational potential energy, which is equal to mgh. And when it reaches the ground, all of its energy has now become kinetic energy, which is 1 over 2 mv squared. So rearrange this for v, and you get that it equals to the square root of 2gh, and that is the speed of the ball right before it's hitting the ground. So 2g cancels out here, and we get that the coefficient of restitution is equal to the square root of the final height over the square root of the initial height. So if we square both sides, then the coefficient of restitution squared is equal to the final height over the initial height. And if we rearrange, then we get that the final height is equal to the initial height times e squared. So we need to find an expression in terms of n. Now personally, I think the easiest way to do that is to just try a few different cases and see if any obvious pattern emerges. So let's consider the very beginning. Our initial height is just the height we start at, which is h. N is equal to 0 since there have been 0 bounces. We then drop the ball and it hits the ground, then comes back up. So our final height is between the first bounce and the second bounce. So n is equal to 1. And we find that h sub 1 is equal to h times e squared, because our final height is equal to h sub 1. And now let's look at what happens after the next bounce. So this time, our initial height is h sub 1, since the ball is coming back down after it got up to that height. It then hits the ground for a second time, meaning the next height is between the second and third bounces, so n is equal to 2. So h sub 2 is equal to h sub 1 times e squared, which is equal to h times e squared, which is equal to h times e to the power of 4. And you'll notice that as n increases, all we're doing is multiplying by another e squared, since h final is equal to h initial times e squared, and h final is just h sub n. And so that means that h sub n is equal to h times e to the power of 2n, and that matches answer D. So next is question 3, which says, two long straight wires with the same current I flowing in the opposite direction are placed parallel to each other with a distance of 2d as shown in figure 1-2. Find the magnitude of the magnetic field H at point P. So for this question, you need to know that the magnitude of a magnetic field is I over 2 pi d, where I is the current going through the wire that's creating the field, and d is the distance from the wire. And the direction of the field is perpendicular to the direction of the wire. You also need to know that a circle with a dot in it means the current is going out of the page, while a circle with a cross in it means the vector is going into the page. So in this case, this one on the left here is going out of the page, while this one on the right here is going into the page. And you need to know the right-hand rule or some other method so that you know the direction of the magnetic field vectors. And if you don't know that, just search it up, because unfortunately it's kind of hard for me to explain the right-hand rule just on like paper like this. But if you search up a video, you can see like it's very easy. And there's definitely videos out there that can explain it way better than I can. So each wire is creating a magnetic field. And so we need to find the resultant magnetic field at point P, which I realize I didn't label. That's this point right here. This is point P. So to start, notice that if you look for this distance L right here, which is the distance from the wire to point P, you form a right angle triangle with two sides of length D. And we can use Pythagorean theorem to find the length of L, which is the square root of 2 times D. And so that means the magnitude of the magnetic field from one of the wires is I over 2 pi, the square root of 2 times D. Also, because both of the wires have the same current and are the same distance from point P, because this right here on the right is the same right angle triangle as the one on the left. So yeah, they have the same current, they're the same distance, and which means the magnitudes of their magnetic fields are the same. However, the direction is different. The left wire goes out of the page, so its field goes to the top left. And the right wire goes into the page, so its field goes into the top right. So given that the magnitudes are the same, the distances are the same, and the angles are the same, right? Because this right angle triangle just has two sides of the same length, meaning these angles must be 45 degrees. And this right angle triangle is the same, so its angles are also 45 degrees. So given that they're all the same, that means that the horizontal components of the two magnetic fields actually cancel each other out. So the resultant magnetic field is just the sum of the vertical components. So to find the vertical component, what we have to do is just multiply by sine of the angle, and we know the angle must be 45 degrees because these two these two sides are the same length. And sine of 45 degrees is something, I guess you just need to know, it's one of the special angles. It equals to 1 over the square root of 2. So the vertical component of the magnetic fields from one of the wires has a magnitude of I over 2 pi 2d. But of course, there are two wires, and they both have the same vertical component. So we multiply this by 2, and we end with I over 2 pi d, and that is choice A. So next is question 4, which says, a sinusoidal wave travels in the positive x direction with a constant speed of 2 meters per second. Figure 1-3 shows a snapshot of the wave at t equals 0 seconds as a function of x. Find the formula for the displacement y at time t. So for this question, unfortunately, I don't think there's any way to be able to confidently answer it unless you know this function right here, which I believe is known as the wave equation. So this allows you to find the vertical displacement of a wave in terms of both x and t, which is needed for this question, since if you look at the multiple choice answers, all of them are in terms of both x and t. So this is the equation. As you can see, there are quite a few values you need to find. Firstly, we have the amplitude, which hopefully you're already familiar with. It is just how far up and down the wave goes from the center. Next, we have the wave number. So the definition of the wave number is that it is how many radians of phase the wave goes through per unit distance. If you want a precise calculation for it, it is 2 times pi over the wavelength. We then have the angular frequency, which you should hopefully know is equal to 2 pi times frequency, or 2 pi over period. And you can also find it using the wave number. You can find it using the wave number, which I show over here. The speed of a wave is equal to the angular frequency divided by the wave number. So you can rearrange this to find the angular frequency. And finally, we have horizontal displacement, which is of course how far the wave is shifted along the x-axis. So if you know all this, you're able to answer this question. So firstly, just by looking at the graph, we can immediately tell that the amplitude is 3, since the peaks are at positive 3 and the troughs are at negative 3. Also, we can find the horizontal displacement. And this is because if you look at x equals to 0 on our graph, you see the y value is also equal to 0 there. And as x increases from 0, the graph starts going up. And that's the exact same behavior as a regular sine function, which means that no horizontal displacement has occurred. So the horizontal displacement is just 0. Next, we can find the wave number. So as a reminder, the definition is how many radians of phase the wave goes through per unit distance. If you look at the graph, you can pretty clearly see that, that the wavelength is 4 meters because we have a peak at 1 meter and the next peak at 5 meters, so a difference of 4 meters. This means that in 1 meter, the amount of radians our phase goes through is 1/4 the entire wave. And an entire wave, of course, has 2 pi radians, so our wave number is 1/4 of that, or pi over 2. And also, you get the same answer if you use the equation for k, which I showed earlier right here, 2 pi over the wavelength. So next, we can find the angular frequency using the speed of the wave, which is given in the question as 2 meters per second, and the wave number. Rearranging this equation right here for angular frequency, we find that it is equal to pi. Also, if you forget the exact arrangement of this equation, an easy way to make sure you got it right is to check the units, like I did here. Angular frequency is in hertz, or per seconds, so if your units work out to anything else, then that means you clearly arranged your equation wrong. So now that we have all of our values, we can plug them into the wave equation. The question wants us to factor out pi, so we end up with 3 times sine of pi over 2 times x minus 2t, which is answer B. So yeah, unfortunately, like I said, I don't know if there's a way to answer this question without just memorizing the wave equation, which I never learned it in school, but maybe it's actually really useful and I just happened to never come across it. If any of you happen to know how you could find the answer with more general principles, be sure to leave that in the comments and you can hopefully help out some other students. So next we have question 5, which says, a movable piston is fitted in a tube as shown in figure 1-4. A speaker near the open end of the tube emits sound waves with a frequency of 555 Hz. When the piston moves from the left end to the right, the first and second resonances are produced at distances of 14 centimeters and 44 centimeters from the open end, respectively. Find the speed of the sound waves. So for this question, you need to be familiar with the idea of resonance. And specifically, you need to know the equation of resonances, which looks like this one over here. Also, you need to know how to find the speed of a wave from its wavelength and frequency. So the question gives us the first and second resonances at 0.14 and 0.44 meters respectively. And using the resonance equation, we find that they are equal to the wavelength over 4 and 3 times the wavelength over 4 respectively. An important thing to keep in mind is you cannot just take one of these equations for either the first or second resonance and rearrange it to find the wavelength. That does not generally work. Instead, what you need to do is take the difference between two resonances and solve for the wavelength that way. If you did try to just use one of the equations, you'll get a slightly different answer for the wavelength for both. Unfortunately, I don't really have a really satisfying reason for why that is the case. That's just how it is when you're using resonances to find the wavelength. And generally, if you have a question like that, they will give you not just one, but two of the resonances so that you can find the difference between them. But anyways, if we find the difference in resonances, it's 0.30 meters, and it is equal to the wavelength over 2, which means our wavelength is 0.60 meters. The question, or sorry, I should say 0.60 meters. The question asks for the speed of the wave, which can be found by multiplying the wavelength by the frequency, which is given in the question. And so you find that the speed is 333 meters per second, and that is answer C. And a quick math tip, 0.60 is just 3/5, and our frequency is just, the letter or the number 5 3 times. So you just turn every digit from a 5 to a 3 to get the answer. Now we're on to section 2, which is a large electricity question. The question reads, consider a circuit shown in figure 2-1 consisting of a resistor R, a capacitor C, an inductor, coil L, a switch S, and a battery with voltage V. At the beginning, the switch is in position B and the capacitor is uncharged. Then the switch is changed to position A. After having been in position A for a long time, the switch is then changed to position C. Answer the following questions. So this is a circuits question, clearly. We have a battery, a resistor, a capacitor, and an inductor. So, of course, you need to know at least the basics of the behavior of all three of these components inside of a circuit. Here's the equations that I used to solve this question. First, current equals to voltage over resistance, which is probably one of the most fundamental circuits equations you'll learn. Next, we have that charge, or Q equals to CV, Q sub C equals to CV. So here Q is the charge in a capacitor, C is the capacitance of said capacitor, and V is the voltage in the capacitor. We also have E, which is the energy supplied by the battery when in circuit with a capacitor, and is equal to CV squared. And then we have the energy stored by the capacitor, E sub C, which is equal to half of CV squared. Then we have the energy stored in an inductor, which is half of Li squared, where L is the inductance of said inductor and I is the current. You could, of course, try to derive these equations, but it's really beyond what I think any high school curriculum would expect you to do. Even when I took circuits in university, the derivations of these equations were only shown as extra material, and they weren't really expecting you to actually know and understand them. So unfortunately, in general, learning circuits does require you to memorize a lot of different equations or spend a really long time understanding how they're derived. But on the other hand, once you know these equations, circuits usually isn't too difficult, thankfully. Also, there's just some things that you need to know about the behavior of capacitors and inductors. Specifically, capacitors act as an open circuit in DC, but only once they're fully charged. Inductors, on the other hand, act as a closed circuit, but again, only once they're fully charged. And the principle of energy conservation applies in this question. Also, one more thing. I have this right here, which is how you find charge in a capacitor using the integral of current with respect to time. You don't actually need to understand this integral. All you do need to understand is that the charge in a capacitor is in fact dependent on the current, just based on the fact that this equation exists. So that's something that you need to remember. So with that all out of the way, we can start answering the questions. So the first part asks, find the current I sub 0 through the resistor just after the switch is changed to position A. So when the switch is in the position A, we have a circuit loop that goes from the battery through the resistor and then through the capacitor. Now, like I said before, capacitors act like an open circuit when fully charged. That would mean that the current through the resistor would be 0. Since there would be no current going through the capacitor and the resistor is in series with it, there would be no way for any current to go through the resistor. But crucially, capacitors are only open circuits when they are fully charged. But this question asks for what happens just after the switch is changed to position A. And the initial question said that the capacitor starts uncharged. So at the start, our capacitor will not act as an open circuit. In fact, it's the opposite. The capacitor will act as a closed circuit, meaning it will have no resistance. As the capacitor charges, its resistance will increase, causing the current through it to eventually become 0. But at the very beginning, in an uncharged state, it will have no resistance. And so the current going through the resistor will just be equal to voltage over resistance of said resistor. So the answer is E. Next is part 2, which says, find the charge on the capacitor after having been in position A for a long time. So now that it's been in position A for a long time, that means the capacitor has had time to fully charge up. So it is just equal to C times V, which is answer F. Next is part 3, which says, find the joule heat generated in the resistor by the time the capacitor is fully charged. So we don't have an equation directly for the joule heat generated in a resistor, but we do have equations for the energy stored in a capacitor and the total energy provided by a battery. And energy must be conserved. So that means that the remainder of energy that is provided by the battery but not stored in the capacitor must instead be generated as joule heat in the resistor. So we take the total energy provided, which is CV squared, and subtract from it the energy stored in the capacitor, which is 1 over 2 CV squared. The remaining energy then is also 1 over 2 CV squared, and that must be the joule heat generated in the resistor. So the answer to this part is B. Next is part 4, which says, at time t equals 0, the switch is moved from position A to position C. How does the current I sub L, which flows into the inductor or coil, change as a function of time? Find one appropriate graph from figure 2-2. So now the circuit has changed. We have a capacitor and an inductor in a loop. The capacitor starts fully charged. So I mentioned before how an inductor acts as a closed circuit, meaning it doesn't have any resistance, and it's basically no different than a regular wire. But just like with a capacitor, that only happens when the inductor is fully charged. At first, an inductor actually acts like an open circuit, so at the very beginning, the current going through it will be 0. So looking at our graphs, that already eliminates 3 options, B, C, and E, since none of them start from 0. Next, we can consider the principle of energy conservation. Our circuit now only has an inductor and a capacitor. Previously, we had a resistor, which dissipates energy through heat. But in this case, we don't have any elements that dissipate energy. That means that all of the energy that was initially in the capacitor must remain in our circuit. Now, the energy stored in an inductor is equal to 1 over 2 Li squared, meaning it depends on the current. That's the equation that I already underlined over here. Inversely, that means that the current depends on the energy, right? If we rearrange this equation to solve for the current, you see that it does depend on the energy. Since the energy in our circuit does not dissipate, that means that the current in the inductor also will not dissipate over time. So that means that option F is eliminated, since if you look at the graph, it just goes towards 0. So we're left with 2 options, A and D. To decide which one is correct, we need to consider the behavior of both the capacitor and the inductor in one circuit. Also, this explanation is a bit heavy, and I don't think it's really necessary to know. I can tell you right now that the answer is a D. This circuit is known as a pure LC circuit, and that's just how they work. The current through the inductor will oscillate up and down. And I'm not actually going to try to explain exactly how this situation works because it's pretty far beyond the material taught in a high school or even in a first-year university class. But I will try to give a satisfying explanation for why D is the correct answer. So we know that the inductor starts with no current going through it, but the current does increase as it gains energy. And by the principle of energy conservation, if the inductor is gaining energy, then the capacitor must be losing energy. And as we discussed before, a capacitor is actually a closed circuit when it has no energy and becomes an open circuit once it's fully charged up. So that means that as it is giving away its energy to the inductor, it is allowing more current to pass through it. And at the same time, as the inductor is gaining energy, it is also allowing more current to pass through it. And so eventually, all of the energy will be passed from the capacitor to the inductor, and there is max current flowing through it. So what happens then? Well, our equation for charge in a capacitor is based on voltage. So right, because it's this one right here, 1 over 2 CV squared is based on voltage. So you might be tempted to, so it's based on voltage, so you might be tempted to say that the energy in the capacitor is just 0. Sorry, I lost track of my script for a second. Let me remember where I was exactly. Right, yeah, so you might be tempted to think that, right, our equation for charge is based, in a capacitor is based on voltage, so you might be tempted to think that it's just 0, and so the correct answer is A. But let's consider this integral right here, which I introduced earlier. Now, we don't actually need to know what the integral means. The only part that matters is that we can see that the charge in a capacitor is dependent on the current. So the amount of current affects the charge in our capacitor. Also, the voltage in a capacitor is dependent on charge, since Q equals to C equals to CV. And if we rearrange that, we see that the voltage in a capacitor is equal to Q over C. And then the energy stored in a capacitor, of course, depends on the voltage. So through this chain, we can see that current does affect the energy in our capacitor. So we have max current going through our inductor, which of course also goes through our capacitor since they are in a loop. And because energy is dependent on current, as we just established, or I guess I should say the change in energy is dependent on current, as we just established, that means that our capacitor must be gaining back some energy. And then if our capacitor is gaining energy, then of course by the principle of energy conservation, our inductor must be losing energy. And we found, of course, that the current going through an inductor is dependent on the energy. So that must mean that the current going through our inductor has to go back down. And therefore, the only remaining possible answer is D. So hopefully that explanation is satisfying. You could learn an even more proper explanation by studying the calculus behind circuits, but that's beyond my expertise and I think it's also beyond what the exam writers expect you to know. But anyways, now that we got that, we can finally move on to part 5, which says find the maximum of I sub L. So we know that the energy stored in our capacitor is 1 over 2 CV squared. Energy must be conserved, which means that the maximum energy in our inductor will be equal to the maximum energy that it can get from the capacitor. So the maximum energy in our inductor will be equal to the energy in our capacitor. Energy in an inductor is equal to 1 over 2 times Li squared. So to find the maximum current I, we just need to rearrange this equation to solve for I. And so we find that I is equal to the square root of C over L times V. And so the answer to part 5 is option A. Next is the section 3 question, which says, an object of mass m is moving with a speed v on a frictionless plane as shown in figure 3. The object reaches at the end of the plane x equals 0 and y equals h at time equals 0 and jumps into the air. There is a slope in the x is greater than 0 region as shown in figure 3. The acceleration of gravity is denoted as g. Answer the following questions. So for this, you need to know the basic kinematic equations. I was taught the so-called Suvat equations, so those are what I'm using. If you aren't familiar, Google Suvat equations and you'll be able to find them very easily. Part 1 says, find the x-coordinate of the object at time t is greater than 0 when the object is in the air. So it says the plane is frictionless, meaning the object does not slow down at any point before t equals to 0, which is when the ball gets to the top of the ramp and flies off. Because the initial velocity is entirely in the horizontal direction, the displacement in the horizontal direction, meaning the x-coordinate is just the velocity times time, and so the answer is D. I also did use this Suva equation right here, where displacement is equal to initial velocity times time plus 1 over 2 times acceleration times time squared. But acceleration, the horizontal, is 0, so it's just the initial velocity times t. And the question gives the initial velocity as v. Next is part 2, which says find the y-coordinate of the object at time t is greater than 0 when the object is in the air. So now we use the same Suva equation, this time in the y direction. In this case, our initial velocity in the vertical direction is 0, since the ball starts by moving along a flat, frictionless plane, and the acceleration in the y direction is just gravity, which is g, and of course it's downwards, which means it's negative. Notice that I used change in displacement rather than just displacement. That's because our y-coordinate at t equals to 0 is h. So we start at h, and this tells us our change in the y-coordinate. So to find the actual y-coordinate, we have to take h and subtract from it the change in y. So we actually have that the y position is equal to h minus 1 over 2 gt squared. And so our answer is F. Next is part 3, which says if v is larger than the speed v sub c, the object does not hit the slope and directly drops to the horizontal plane at y equals to 0. Find the expression of v sub c. So we want to find the speed such that our ball takes this path right here in the dashed line. It flies off at the top of the ramp and it does not touch the ramp at all. It just lands at the very bottom right here. Put another way, we want the ball to travel this distance in the x direction, call it L, in the same time as it takes for the ball to fall a height of h. So we have this angle theta right here. So we can find that L is equal to h over the tangent of theta, right? Because tangent of theta is opposite over adjacent. And so we have this expression that we found in part 2 for the ball's position in the y component. Notice it does not at all depend on the initial speed, since the initial speed is entirely in the horizontal component. Also, we said the ball has to fall a height of h. And since we're starting from a height of h, that means that the y-coordinate of our ball has to equal to 0. So if we rearrange this equation, we can find that the time it takes for the y-coordinate to equal to 0, and that is the square root of 2h over g. We also have this expression from part 1 for the ball's x component. We want the ball to travel a distance of L, which we found is equal to h over tangent theta previously. And we want to do it in the time it takes for the ball to reach the floor, which of course we just found right here. So we can plug in all of these values and then rearrange to solve for the velocity. You also need to rationalize the denominator, right? We have a square root in the denominator, but none of the options given have a square root in the denominator. So when you do that, eventually you find the answer is the square root of 2gh over 2 tan theta, which is option C. Then we have part 4, which says if v is less than v sub c, the object hits the slope. Find the x-coordinate of the impact point. So if we look back at our diagram, we have this ramp and we have the trajectory of the ball with a dashed line. Previously, we were looking at the case where the ball flies over this entire ramp and lands at the very bottom. Now we're looking at the case where the ball hits the ramp, meaning the trajectory of the ball intersects with the ramp. So if I were to redraw this, I don't know if you guys saw, there's an Amber Alert going on. If I were to redraw this line, it would look something like this now. So at some point along the ramp, the trajectory of the ball would match the ramp. So what we want to do is find an equation for this ramp and make it equal to an equation for the trajectory of the ball. So first let's find an equation for the line for this ramp. So we know that the y-intercept of the line has to be equal to h, since on the diagram the y-axis is right where the ramp starts, and the ramp starts at a height of h. So then, to find the slope, we can use rise over run. So the rise goes from 0 to h, and the run goes from L to 0, right? So if we look at the diagram, the rise, here the y-coordinate is 0, and at this point it's h, while here the x-coordinate is L, and here it's 0. So we do rise over run. We find that the slope is equal to negative h over L, and from when we found previously that h over L is equal to tangent theta, meaning that our slope is equal to negative tangent theta. And so the equation of our line, or the equation of the ramp, is that y equals to h minus x times tangent of theta. We also have from part 2 that y equals to h minus 1 over 2 gt squared. So since these both equal to y, we can make them equal to each other. But there's a problem. This expression has t in it, which is not in any of our multiple choice solutions. It also doesn't have v in it, which is in all of the solutions. So clearly we have to rewrite t in some other terms. So we have another equation, right, which is that x is equal to vt, which is from part 1. And if we rearrange, we find that t is equal to x over v. So we could plug that in for t into our equation. Then, because we're adding h on both sides, we can just cancel them out, right? This side has positive h, this side also has positive h. Those cancel out. And then we cancel them out. And then if you bring all the terms to one side and factor x out from it, we get that x times all this stuff in the parentheses is equal to 0. So firstly, this is of course true when x equals to 0, right? We make x equals to 0, this 0 multiplied by all that. This doesn't matter anymore because you're multiplying it by 0. And that of course happens when t is equal to 0, since at that point the object is at the very top of the ramp. So of course it is touching the ramp. The next time it occurs is when all this stuff inside of the parentheses is equal to 0. So if we take that and make it equal to 0, and then you rearrange to solve for x, which I'm not going to go through every step. You can pause and look at my rearrangement if you want to make sure you got it right. So you rearrange to solve for x, and you find that x is equal to 2 times v squared over g times tangent theta, which is answer E. Next is question 4, which says, a non-adiabatic cylinder with cross-sectional area A is placed at normal air pressure and is filled with an ideal gas as shown in figure 4a. The cylinder is closed by an adiabatic piston with mass m. The pressure of the air is P and the temperature of the air is T. In equilibrium, the height of the piston is h from the bottom and the temperature of the gas is T. An object of mass big M is placed on the piston, and the height of the piston becomes h1 in equilibrium as shown in figure 4b. The acceleration of gravity is denoted as g. Answer the following questions. So to answer this, firstly, you need to know what adiabatic means. It's basically just another word for insulated. So if you have an adiabatic container, then energy cannot pass in and out of the container. So meaning that if, say, you have hot water inside of an adiabatic container, that water will stay hot. If your container is non-adiabatic, however, then the water will transfer energy to its surroundings, and eventually it will be the same temperature as its surroundings. Also, you need to know that that work done by a gas equals to pressure times the change in volume, the classic ideal gas law, PV equals nRT, and that pressure equals to force over area. And you need to know how to draw a basic force diagram. At least that's how I answered this question. So to start, let's consider what values we have and what values are constant for our gas. The question didn't say anything about our ideal gas escaping, so our number of moles must be constant. R is, of course, literally a constant, so that won't change. And our temperature is actually also a constant, and that's because the question says the cylinder is non-adiabatic. That means that energy can be transferred through the walls of the cylinder, so the temperature of the gas will always just be the same as the atmospheric temperature. Notice I put like an asterisk right here, and that's because later on in the question the conditions change and the temperature is no longer constant, but for now we can say it is. So next let's draw a force diagram of the initial conditions, which I will call condition 0. So we have two downwards forces. Firstly, the force of gravity, which is just m times g, right? M is the weight of the cylinder. We also have the force of air pressure, which I denoted as F sub P right here. And then to balance that, we have because question says it's in equilibrium. So to balance that, we have the force of the gas, which is F sub gas comma 0, which is equal and opposite to the sum of the forces of gravity and air pressure. And keep in mind that the atmospheric pressure doesn't change, it's always P. So the force of the atmospheric pressure is constant. So pressure equals to force over area. So the force of atmospheric pressure is P times A, which is the cross-sectional area of the piston. Now F sub gas comma 0 is then PA plus mg, since it's balancing out the two downwards forces. So to find the pressure of the gas, we just divide that by A, and it equals to P plus mg over A. And then the volume of the gas is just equal to A times H, right? Because A is a cross-sectional area, H is the height, and so that gives us the three-dimensional volume. So we can plug all of that into PV equals to nRT, and we get this expression right here. PA plus mg times H equals to nRT. All right, now let's consider condition 1. So just now we did condition 0, which I guess you say is condition A because it's given as diagram A. Now we're doing condition 1, which is given as diagram B. So we've added the mass of big M on top of the piston. So now the force of gravity is small m plus big M times G. And so that means that the force of the gas pushing up has to increase to accommodate, because again, it says it's still in equilibrium at H1. And of course, the force of air pressure is still the same since, like I said earlier, it is just a constant. So we find P sub gas comma 1 in the same way that we found it before, except instead of just mg, we have small m plus big M times G. And so that means that the pressure gas this time is now P plus small m plus big M times G over A. And this time the volume is now A times H sub 1. So we plug that into PV equals nRT, and we get this expression right here. PA plus small m plus big M times G times H1 equals to nRT. And, of course, the expression we found earlier, this one, also equals to nRT. And so we can make these two expressions equal to each other. And so we do that. And then we just rearrange to solve for H1, which is really easy. We just take all this and divide both sides by it. And we get that H sub 1 is equal to PA plus mg over PA plus big M plus small m times G, all multiplied by H. And that matches option B. So next is part 2, which says, find the work done on the gas by the air when the height of the piston changes from H to H1. So notice that it says the work done on the gas by the air. So we are using the pressure and volume of the air, not the pressure and volume of the gas. So the pressure is, of course, just P, because we're talking about the air and the atmospheric pressure is P. The change in volume is the difference between A times H and A times H sub 1. Also keep in mind that because the air is pushing into the gas, causing the gas to shrink, the work done by the air must be positive. So that's why for change in volume, we do A times H minus A times H sub 1. Since A times H sub 1 is clearly smaller than A times H, since H sub 1 is clearly smaller than H, since there's more mass pushing down in condition 1. So we have that work equals to PA times H minus H sub 1, right here. And so then we plug in the expression for H sub 1 that we found in the last part. You can then factor out H from both the terms in the parenthesis. Also, if you combine the terms of the parenthesis into a single term, so right now here we have 1 minus all this, and then if you take 1 and multiply you multiply it by PA plus small m plus big M times G, and also divide it by that, so you get one single fraction, then you'll see that a lot of stuff in the numerator cancels out, right? We have PA here and negative PA here, so those cancel out. And then if you expand these parentheses right here, we have we have positive small g and negative small g. Those cancel out as well. And so we end up with just big M times G times PAH divided by PA plus small m plus big N times G, and that matches option F. So next is part 3, which says, we then cover the system with adiabatic walls and remove the object with mass m. In equilibrium, the height of the piston becomes h sub 2. Find the temperature of the gas. So now, because we have added adiabatic walls, meaning isolating walls, the temperature is no longer constant because it cannot exchange heat with its surroundings. Also notice that by removing the mass big M, the conditions are the same as they were in condition 0, except for the adiabatic walls. So we can compare condition 0 with this new condition, condition 2. So in condition 0, we had pressure equal to P plus mg over A, volume equals to A times H, and so nRT equals to PA plus mg times H. And that's what we found earlier in part 1. Now in condition 2, we actually have the exact same pressure. And that's because if you were to make a force diagram, like I did right here, you'll see that it's exactly the same as the force diagram in condition 0 that we made earlier. We have mg, and we have the force of air pressure going down, and thus the force of the gas is pushing back equal and opposite. This is exactly the same as our force diagram for condition 0. So the force of the gas pushing up must be the same, meaning the pressure of the gas must also be the same. And we also have the volume now, which is A times H sub 2, and we can plug this into PV equals nRT, though of course now we have T sub 2 because we're trying to find this new temperature of the gas. So now with this, we can relate the two expressions to each other by turning them each into one fraction. And if you're wondering how I did this, you can see that if you have, PV equals to nRT, or in this case, what we found as PV equals to nRT, if we divide both sides by this, then this side just becomes a fraction, and this side just becomes 1, right? Because we're dividing it by itself. And we can do that with the other, with this other expression right here, and you also just make it equal to 1, and since they both equal to 1, they now equal to each other. So with that, we're able to make these equal to each other, and then if we rearrange to solve for T sub 2, you'll see that many things cancel out, right? We have N in both, we have R in both, we have PA plus mg in both, and so the only things that are left are T, H, and H2. And so we find that T sub 2 is equal to H sub 2 over H times T, and that matches option E. So next is question 4, which says, we then remove the adiabatic walls. In equilibrium, the height of the piston becomes H sub 3. Find the expression of H sub 3. So since we have removed the adiabatic walls, the temperature of the gas just goes back to being the same temperature as the air, which is of course just T. And so what you might realize is that now the conditions are exactly the same as condition 0. We have the same temperature, we have the same pressure. That must mean that our volume is also the same. And you can quickly prove this with PV equals nRT. If you rearrange for V, you see that it equals to nRT over P, and all of these values are the same now as they were in condition 0. So that means that H sub 3 must just be equal to H, and so the correct option for question 4 is A. So finally we have part 5, which is an optics question. It says a light ray of wavelength, I think that's lambda, I don't really remember, traveling through air is incident on a flat, thin soap film at an angle theta to the normal, as shown in figure 5. The thickness of the film is D. The path of the light ray is bent towards the normal in the film with the refraction angle phi. We assume that the index of refraction of air is 1 and denote the index of refraction of the film by n. Answer the following questions. So for this, you need to know some of the basic optics laws. We have what I believe is called Snell's law right here, which is that n sub 1 times sine of theta sub 1 equals to n sub 2 times sine of theta sub 2, where n is the refractive index of the material the light is traveling through, and theta 1 and 2 are the angles of incidence. The refractive index is found using c over v, where c is the speed of light in a vacuum and v is the speed of light in the medium that we're finding the refractive index for. F sub n1 equals to F sub n2 just means that when a beam refracts from one medium into another, the frequency does not change. And of course, the speed of a wave is equal to its frequency times its wavelength. Also, the question says that the index of refraction of air is 1. That's the same as the index of refraction in a vacuum. In reality, the index of refraction of air is a little bit higher than a vacuum, but it's so close that it's usually approximated to be the same, except in very precise cases. Also, you cannot have a refractive index less than 1, which means that our refractive index n must be greater than the refractive index of the air. The path difference, which is this right here, is equal to the difference in optical path lengths of two rays. For constructive interference, the path difference has to be n times the wavelength, while destructive is equal to n plus 1 over 2 times the wavelength. But notice there's a big red asterisk right here. That's because these two conditions actually swap if one of the rays is reflected off the surface of a material with a higher refractive index than the material it was passing through. Because when that happens, the ray has a phase shift of pi. Now, optical path length is equal to n times d, where n is the refractive index and d is the actual distance that the ray passes through. So here's an example to illustrate how optical path lengths work. So here in this first example, the refractive index is just equal to 1. And in this distance, the light is able to traverse a total of 3 wavelengths. So the optical path length, or OPL, is equal to n times d, which is 1 times 3, and that equals to 3 total wavelengths. Now here we have the same physical distance, but now the refractive index is 2. That means that the OPL is equal to 6. So in the same distance, the light traversed 6 wavelengths instead of just 3. And the reason why this matters is because, for instance, constructive interference requires both waves to meet at their peaks at the same time. So here we have a refractive index of 1.5, which means that the OPL is now 4.5. So now in the same distance, the wave, as you can see, ends in a trough rather than ending at a peak like these last two waves did. So this wave here with the refractive index 1.5 would have destructive interference with the other two waves if they were to meet at the very end over here, while these two waves would have constructive interference with each other if they were to meet at the ends. So that's why for path difference, you use the optical path length rather than just, the length traversed. Also, apparently this equation right here is one that's just taught or just given to students. The OPD, which is the optical path difference, is equal to 2nd times cosine theta. And that's for the specific situation in this question where you have a film and a beam of light that reflects off the film plus a beam of light, or I should say a ray of light, that refracts into the film and then refracts out at the top. I don't know if this is actually something that's taught or given to students or not, but I thought I'd include it here just in case someone recognizes it. I will show how to derive this equation later on anyway, so don't worry if you don't know what this is. Also, you technically need to be familiar with some of the principles of slit diffraction, and as you can probably guess just by looking at the diagram in the question, you need to know a bit of trigonometry. Oh, and also, finally, you need to be familiar with the idea that if you have two parallel light rays, and one is refracted into a different medium, the optical path length of the parallel component of the refracted ray is equal to the optical path length of the parallel component of the non-refracted ray. And specifically for this question, that means that the optical path length of PC is equal to the optical path length of AQ. Now, with all that, we can start answering the questions. So first is question 1, which says, find the wavelength of the light ray in the film. So we know the frequency in both mediums is equal. We also know that the speed of the wave in the film is equal to, and let me actually scroll down to that. Yeah. So we know the speed of the wave in the film is equal to the speed of air in air divided by the refractive index. and that's from one of the equations that I gave. The speed is just equal to frequency times wavelength. And so, and the frequencies are the same, so they cancel out. And we get that the wavelength in the film is equal to the wavelength divided by n, and that is option B. So next is question 2, which says find the relationship between theta and phi. So for this, you just use Snell's law and immediately find that the correct option is D. And next is part 3, which says if a certain condition is satisfied, constructive interference occurs between the light reflected at C and the light traveling through the path ABC. The condition is expressed using a non-negative integer m. Find this condition. So I have to admit something here, which is that I never actually learned about waves in optics in high school or in university. I have, of course, studied it on my own, otherwise I wouldn't be able to answer this question for you all. But what that does mean is that I don't really know what is considered obvious or common knowledge for a physics student. So my explanation from here on, and also maybe up to this point, might be really long-winded and pointless because I'll be explaining things that maybe you already learned and is assumed to be, obvious or just given information. I'm not really sure. So anyways, we want constructive interference. So that means that we need the path difference. We need to find the path difference between our two rays. Usually constructive interference requires that the path difference be equal to an integer multiple times the wavelength. So in this case, the question says that the integer is m. But as I mentioned before, these conditions can actually swap depending on what sort of reflections your rays go through. And by these conditions, I mean the conditions that for constructive, it's integer times wavelength, while for destructive, it's integer plus 1/2 times the wavelength. So in this case, the ray on the right, meaning the one that just reflects off of C, is passing through air and then reflects off of the film. The film has a higher refractive index than air. So that means that the ray on the right undergoes a phase shift of pi. So actually, we don't want the path difference to be equal to m times the wavelength. We want it to be equal to m plus 1/2 times the wavelength. But that assumes our other ray does not undergo any phase changes. So that ray goes into the film, which does not produce any phase shifts. It reflects off of the bottom at point B, and then comes back out at the top. At point B, the ray is traveling through the film and then reflects off of the boundary with air at the bottom. Air has a lower refractive index than the film, so there is no phase shift in the reflection at point B. So because only one of our rays undergoes a single phase shift of pi, this right here is in fact correct. So now we actually want to find the difference in the two paths. So to do that, we need to figure out which parts of the path are identical for both rays and which parts are different. So firstly, we can clearly see that once the rays reach point C, they have identical paths. Since both rays, you can say, combine at C and just become a single ray. So we know the differences in paths end there. The next question is where the differences in paths start, and unfortunately, if you haven't studied optics before and came across a question like this, it's not so obvious. So let's consider these two rays, the left ray and the right ray. The left ray I drew here in blue and the right ray I drew in red. So to start, it is assumed that these two rays come from the exact same source. And that's because if they didn't, then we would have no way of comparing their optical path lengths. If the left ray started from, say a source over here, while the right ray started from, another source, say all the way over here, we'd have no idea what the difference is in optical path lengths in this entire region. And so it'd be impossible to compare these paths, and the question wouldn't even make any sense. Also, two different sources can transmit light with different wavelengths, or they can have, relative phase differences, meaning, one of them, like one of the sources is, just like the waves do not have the same crest and trough, something like that. Basically, this question, or really any other thin film interference question, wouldn't make sense unless the rays come from the same source. And that is known as coherence, when you have two rays that don't have any relative phase differences. So if they're coming from the same source, that means they're also starting at the same place. So let's say that our source is, this point right here, and these rays are coming down like this. Now, what you'll realize is that these rays are actually not parallel like they appear to be in our question. In order to strike different parts of our film, these rays must have some angle between them when they leave the source. And since there's an angle, they're not actually parallel. But the thing is, this is a thin film interference question. And the important thing about that is that thin film interference happens on a really tiny scale, like nanometers or micrometers. So that means that this angle right here is incredibly tiny. It's so tiny, in fact, that it is acceptable to approximate these two rays of light as actually just being parallel to each other. If you learned about slit diffraction, then this concept might be familiar to you. So we assume that these two rays are parallel, and of course they come from the same source, which is radiating light rays. So that means that these two light rays have traveled the exact same distance, meaning they are still in phase up until this line right here that crosses through points A and point P. At this point, both of the rays have traveled the exact same distance through the same medium, so there is no path difference. And so when calculating the path difference, this is our starting point. And just to reinforce that, let me redraw this source here a little bit. So like we said, they come from the same source, and they're not actually parallel, but we assume them to be parallel. So the way that would look is basically we have both of these paths, and then we have our source right here. And the source radiates these rays outwards, meaning that our rays are perpendicular to the surface of the source. And so what you'll see now is that this distance from the source to point A is the same as this distance from the source to point P. So that's why we can say that that both of the rays have traveled the exact same distance and of course through the same medium. So there is no path difference up until we reach points A and point P. So with that, we can begin to calculate the path difference and answer this question. And let me remove all this extra stuff so it doesn't get in the way. So let's first consider the ray on the left, which is the one that refracts into the film. So it has the same OPL with the ray on the right up until point A. After that, it travels from point A to point B, and then from point B to point C. And of course, that's within the film, so the refractive index is n. Therefore, the OPL on the left, or the OPL for the left ray, is n times the length of AB plus the length of BC. And now let's consider the ray on the right. So this one has the same OPL with the left ray until point P. After that, it travels from point P to point C. So the OPL of the right ray is just equal to the distance from P to C. And of course, we have to multiply that by the refractive index. But in the air, the refractive index is just 1 since it's traveling. So, it doesn't actually do anything. So now we can find the optical path difference by taking the left beam and subtracting the right beam. And as discussed earlier, in order to find constructive interference, this has to equal to n plus 1/2 times the wavelength. And to be clear, we are talking about the wavelength in air, not in medium. And so we end up with something like this. And also, technically path difference has absolute values, but if you look at our diagram, clearly the path from A to B and then B to C is greater than the path from P to C. And so as long as we're subtracting PC, we can just ignore the absolute values. But the thing is, if you look at the multiple choice answers for this question, this doesn't match any of them. So that means we need to do a bit more work. So for this, we need to consider an important principle of optics, which I mentioned earlier. So point P, if we look at our diagram, is the point on the right ray that is perpendicular from point A on the left ray, right? So point P, if you draw a line perpendicular to the right ray from point P, it goes to point A. And point Q is the point on the left ray that is perpendicular to point C. And so what this means is that the optical path length of AQ is equal to the optical path length of PC. Okay, so during my explanation, I said that the optical path length of PC is equal to AQ, and that's because they're perpendicular to each other. And that's true, but I realized I didn't actually provide any proof of that, so I'd like to actually prove it now so that you can all see why that works and not just that that's a fact. So we have this diagram here, right? It's the same diagram as the question. Now, in order to be able to prove that the optical path length of AQ is equal to the optical path length of PC, you're going to have to use this formula right here, n sub 1 sine theta is equal to n sub 2 sine phi. I believe that's called Snell's law. In this case, I'm saying that outside the refractive index is n1. Of course, in our question, the refractive index in the air is just equal to 1, but I want to make it more general, so I'm using n sub 1. And then the film is n sub 2, and I guess I didn't mention it, but just like the question, oh, actually, sorry, other way around. N sub 2 is greater than n sub 1. So in our question, the refractive index of the air is just 1, while the refractive index of the film is something greater than 1. So we have n sub 2 is greater than n sub 1. So if you know that, then you can actually prove that the optical path length of PC is equal to the optical path length of AQ. I would recommend that you try to do it on your own first. And actually, I guess I can give a hint. The way we're going to do it is we're going to consider the fact that both PC and AQ are part of these right triangles, and both of those right triangles share this side right here. They both share the side AC. And so with that, you can prove that they have the same optical path lengths. But anyways, let's start. So firstly, one thing you have to realize is these two beams, this left beam, which is in blue, and the right beam, which is in red. Sorry if you could hear that, there's vehicles outside. They are parallel to each other. And if they are parallel to each other, that means this line from P to A, it's perpendicular here, which is given in the question, but it also must be perpendicular on this side, right? Because you have two parallel lines, you draw a perpendicular line, right? If you have two lines that are parallel, and you draw a line going out from one of them that's perpendicular to it, it must also be perpendicular to the other line because they're parallel. That's just how it works. So we know that this is perpendicular. And so because of that, what we know is this entire angle right here, this whole thing, must be equal to 90 degrees, or actually, sorry, that's not why it is, but okay, this whole angle right here in red, this must be equal to 90 degrees plus theta, right? Because here, this is clearly a right angle, and then we also have theta, and so that entire angle is 90 plus theta. And then, so if this whole angle is 90 plus theta, and we have this right angle here, then that means that this angle on the inside here must be 90 plus theta minus 90, which means that this angle is just theta. And I have that written over here, angle PAC, which I don't know if this notation is common everywhere. What this means is it's the angle between PA and C, and the one in the middle is the one where you find the angle in. So we have PAC, A is right in the middle, so we're finding the angle at A. And so we find that that just equals to theta. So with that, we can take sine of theta, and it's opposite over hypotenuse. Opposite is the length PC, hypotenuse is the length of AC. And so we find that the length of PC is equal to sine theta times the length of AC. And then what we're going to do is we're just going to multiply both sides by n sub 1, which is the refractive index in the air. And we're multiplying both sides by the same thing, so this expression is still valid. Okay, so we did the first part. We found the length of PC, or the optical path length, right? Because this is the optical path length, right? It's the actual length times the refractive index. So we found the optical path length of PC in terms of AC. Now let's do the same thing for AQ. So right here I have that the angle QAC is equal to 90 minus phi. And the reason why is because this right here is clearly a 90-degree angle. And so this angle right inside here must be that 90 degrees minus phi, because phi takes up this part, that angle takes up the remainder, and so that angle QAC is equal to 90 degrees minus phi. And so what that means is if we want to find the angle ACQ, which is this angle right here, we consider the fact that, this is a right triangle. So the angles inside must total to 180 degrees. We subtract 90 degrees, which is this right angle over here. We then subtract this angle right here, QAC, which we found to be equal to 90 minus phi. So we have 180 degrees minus 90 degrees minus 90 minus 5 degrees. So 180 minus 90 again, we have 0 degrees. Then we have minus negative phi. So that angle is just phi. So this angle right here, ACQ or QCA, is phi. And so with that, we can find the sine of phi, and that equals to the length of AQ, which is opposite, over the length of AC, which is the hypotenuse. And so we find that the length of AQ is equal to sine of phi times the length of AC. And then once again, I'm going to multiply both sides by the refractive index. This time we're inside the film, so the refractive index is n sub 2. We have n sub 2 times the length AQ is equal to n sub 2 times sine phi length of AC. And n sub 2 AQ is, of course, the optical path distance of AQ. So now what we can do is we can actually use Snell's law. So we have n sub 2 sine phi right here, and we know from Snell's law that n sub 2 sine phi must be equal to n sub 1 sine theta. So now we can say that n sub 2 length AQ is equal to n sub 1 sine theta length of AC. And we found previously that n sub 1 sine theta length of AC is equal to n sub 1 length PC. And so we find that n sub 2 length of AQ is equal to n sub 1 length of PC. And by the way, this line above just means length. I don't know if that's common notation, but that's what I learned in school. And yeah, so we have that the optical path length of AQ is equal to the optical path length of PC, which is, what we are trying to prove here. So hopefully that's helpful. Like I said, maybe that's just like taught to be a fact, but hopefully this proof is useful to you guys. So what that means is that we can rewrite the length AB to be the length of AQ plus QB. And then we have NAQ plus N times QB plus BC minus PC. And as we just discussed, N times AQ is equal to PC, which means that these two terms now just cancel each other out. Because here we have plus NAQ and here we have minus PC. They equal to each other, so we can just remove them. And so we are left with this. And then now if we just divide both sides by n, this n is removed. On this side, the n appears over here. And we get that QB plus BC is equal to m plus 1 over 2 times the wavelength over n, and that is option A. So lastly is part 4, which says, find the expression of D when the condition in part 3 is satisfied and constructive interference occurs. So we need to rewrite the expression we just found in terms of D and phi. So I'm actually going to go back a few steps to when our expression looked like this right here. So we did find this earlier. This was I just copied it from here. And the reason for that is that we can find the lengths of AB and BC in terms of D and phi really easily. So if you take cosine of phi, it equals to D over the length of AB. And so the length of AB is just D over cosine of phi. And clearly BC is the same length as AB, since in a reflection, the angle of incidence is equal to the angle of reflection. So if we were to draw like a line here that's perpendicular to the bottom, this angle right here is equal to this angle right here. And so AB plus BC is equal to 2D over cosine phi. So now we just need to find PC in terms, we need to find the length of PC in terms of D and phi. So we know from before that the length of PC is equal to the OPL of AQ, which is n times the length of AQ. So now we need to find the length of AQ. Now, if we look at the diagram, we can see that AQ is part of this right-angled triangle along with the sides AC and CQ or QC. So we can find, and so firstly, we can find the length of AC quite easily. So if you take the tangent of phi, then the opposite, right, because tangent is opposite over adjacent, the opposite is this distance right here. This is clearly just half of the distance of AC. And the adjacent is just D. And so if we rearrange, we find that the length of AC is just equal to 2D tangent of phi. Next, the angles. So this angle here is phi, which then means, let me draw this in a different color so it doesn't get too difficult to follow. If this angle is phi, then this angle right here, that must be 90 degrees minus phi, right? Because this right here is a right angle. Part of that angle is taken up by phi, so the remainder is 90 minus phi. And sorry, I lost my place on my script. Give me 1 second. Okay, yeah, so we know that this angle right here is 90 minus phi. And so if we know that, the way you can do, so we can, we can find this angle then very easily, because obviously this is a triangle. Angles in a triangle add up to 180 degrees. So we just take 180, we subtract 180 degrees, we subtract from it 90 degrees, which is the right angle. We also subtract from it this angle right here, which is 90 minus phi. So we have 180 minus 90 degrees minus 90 degrees minus phi. So minus 90 minus 90, that's minus 180, minus negative phi, just equal to phi. So this angle right here is just phi. So now, what we can do is, so since we have phi here, we can take sine of phi using this angle. And if you do that, you find that sine of phi equals to the length, the length of A from A to Q divided by 2D tan theta, right? Because 2D tan theta is the length of AC, which we found earlier. And so if we rearrange that, we find that the length of AQ is equal to 2D tan phi sine phi. Did I say theta earlier? I meant to say phi. 2D tan phi sine phi. And so then, since we were doing this because we wanted to find the length of PC, we find that the length of PC is equal to n 2D tan phi sine phi. And so now we can go back to this equation that we had for the optical path difference, and we can plug in the values that we found. So we found that the length of AB plus BC is equal to 2D over cosine phi, and we just found that the length of PC is equal to n 2D tan phi sine phi. So we plug those in, and then you'll see that we can factor out n2d from both terms. So we do that here. Then we have tangent phi right here, and you can rewrite, if this is a basic trigonometry thing, you can write tangent phi as sine phi over cosine phi. And then we have sine phi and sine phi here, so that becomes sine squared phi. And then now both of those terms are being divided by cosine phi, so we can combine them into one fraction. And then you need to use the Pythagorean identity here, because 1 minus sine phi or sine squared phi is equal to cosine squared phi, right? And that's from the Pythagorean identity, which is that sine squared theta plus cosine squared theta is just equal to 1. And if you rearrange that, you'll get that 1 minus sine squared theta is equal to cosine squared theta. So here we have 1 minus sine squared phi. That is equal to cosine squared phi. And of course, we're dividing it by cosine phi, so one of the cosines cancels out, and we end up with n2d cosine phi. And again, apparently this is just given as a fact to students in some places. That's kind of what I gather from looking on the internet. I'm not certain. But maybe that isn't the case for you, in which case hopefully me deriving this is helpful. But going back, we need this to equal to m plus 1 over 2 times the wavelength, and then we rearrange this to solve for d, which is of course what the question is asking for. Now in the question, none of the options have this 1 over 2, and so the way we fix that is we multiply both the numerator and the denominator by 2. So here we multiply by 2 and we put it into the parenthesis, so m becomes 2m and 1 over 2 just becomes 1. And then here at the bottom we already have a 2, we multiply by 2 becomes a 4, and so we get 2m plus 1, d equals to 2m plus 1 times the wavelength over 4n cosine phi, and that is equal to option B. So that is it for this exam. I hope you found this helpful. If you have any questions about this exam, leave a comment and I will try to help if I can. And if you're writing the MEXT exam soon, then good luck and have a good day.